Hi and welcome back to Spacetime Diaries. Today we are diving into the concept of the derivative and exploring its various forms as they appear in physics. We'll start with the fundamentals and work our way through the different types of derivatives used in physical theories. Whether you're revisiting basic ideas or looking to deepen your understanding, this discussion will offer a clear and concise guide. We know that the straight line has a constant slope which tells us how steep the line is. But what if we want to define the slope of a curve? That's where the ordinary derivative comes in. By considering 2 points, say at x and x plus h, looking at their corresponding values f of x and f of x plus h along the y-axis, we can define a ratio. This ratio tells us how much the function changes in the target space as we move along the x-axis. Essentially, it's the rate of change of the function. However, as we move along the curve, we notice that the slope isn't constant. It changes depending on which 2 points we choose. To capture this change, we take these 2 points and bring them closer and closer together. In the limit, as the points merge into a single point, the ratio approaches a specific value. That value is what we call a derivative, and it can be said that it is the slope at a point. Let's check if our definition is correct. We try here to compute the derivative of square root of x . It comes out to be 1 by 2 times square root of x. I now ask you to put the values of the 2 to see if our definition is correct. Now you might wonder why this works. Let's zoom in on a curve. As we bring the 2 points closer together, the segment of the function between them starts to resemble a straight line. At this tiny scale, the function behaves almost linearly, which allows us to define a clear, unique slope at that point. This is precisely why the derivative effectively gives us the slope of a function. Let's look at another example. Imagine zooming in on the corner of a square. No matter how much we zoom in, that corner never smooths out. It always retains its abrupt change. Because the sudden change in the direction cannot be approximated by a straight line, the derivative is not defined at that point. So our definition does not work for such functions. Now, a function can depend on more than one variable, which is often the case. For example, consider the temperature in a room. Each point in the room is defined by 3 coordinates, and at every point a temperature value is assigned. Let's look at a graph of a function that takes in 2 values and outputs a single value. You can think of this function as representing the temperature on a 2-dimensional surface. Now, how do we define a derivative in this multivariable context? We can start by slicing the surface along a specific direction. For example, imagine placing a plane along y-axis at a fixed value of x. The intersection of this plane with the surface gives us a curve. By taking the derivative of this curve, we can measure how the function changes in y direction while x is held constant. This is known as the partial derivative of function with respect to y. Similarly, we can define a partial derivative with respect to x as well. The partial derivative along one coordinate doesn't capture the full concept of a slope we discussed for a simple curve, because here we're dealing with a surface. What if we want to take derivative in an arbitrary direction? Let's work towards extending the idea of a derivative to any direction on the surface. Let's take another surface and consider 2 planes, and compute both partial derivatives at the point where these planes intersect, capturing how the function changes in both directions, x and y. Notice that the partial derivatives not only provide the slope values on the surface, but also indicate the direction of change for each coordinate. By combining these partial derivatives, we can define a new derivative that gives the slope of the surface in the direction of maximum change. This is known as the gradient. The gradient is extremely useful because it is a vector that points in the direction of the steepest ascent. Moreover, we can project this vector onto any other direction to compute the derivative in that specific direction. Taking gradient of a scalar function transforms it into a vector field, assigning both a magnitude and a direction at every point. For example, consider the temperature distribution in space as a scalar function. Its gradient represents the rate of change of temperature, indicating the direction of the steepest temperature increase from any point as well as the magnitude of that change. Let's solve an example to see how this works in practice.